Welcome to our last lecture for Chapter 4, specifically 4.6, Polynomial Inequalities and Rational Inequalities. You might want to take a little break and do a tick-tock dance like I'm doing in my picture here. I think I did that in the last one too, so let's I'm not moving on. There we go. Today what we're going to do is just look at how do we solve polynomial inequalities and then also how do we solve rational inequalities. Quadratic inequality can be written in the form ax squared plus bx plus c is greater than 0. And that's all we're talking about is inequalities. Equations have an equal sign. Inequalities have an inequality sign, which is either greater than, less than, greater than or equal to, or less than or equal to. Okay, so that's what we're talking about when we're talking about inequalities. Is greater than, less than, greater than or equal to, or less than or equal to. A quadratic inequality is simply one type of polynomial inequality. X squared plus 2x minus 3 is greater than 5 would be an example. But there are examples of other polynomial inequalities. For example, negative 2x to the fourth minus x squared minus 2 is greater than 4. Or 3/4 x plus 6 is less than or equal to 0. And the final example that we have here is 8x cubed plus 2x squared is less than 6x plus 5. These are all examples of polynomial inequality. So let's look at an example to understand this better. X squared minus 3x minus 4 is greater than 0. Let's look at the graph of x squared minus 3x minus 4, and this might give us some insights into what we're trying to figure out. Here we have the graph. We know that it's a quadratic. We have a parabola that's facing up because our a is positive. We can see here that we have zeros at -1 and 4 because the graph crosses the x-intercept at -1, 0 and at 4, 0. And if we think about it, what is this asking us when we look at this original question? Solve x squared minus 3x minus 4 is greater than 0. So we're actually asking, where is this function positive? Where is it greater than 0? And if you think about it, if you look at it, this is where the function is above the x-axis. The blue parts of the graph that you see here are where this function is greater than 0 or positive. If we look at the green parts, this is where the function is actually negative. The y values are negative because they are below the x-axis. We're going to kind of use this general idea about positivity and negativity to solve these problems. And so we might have to manipulate equations. For example, if this original problem said x squared minus 3x minus 2 is greater than 2, we would have subtracted 2 from both sides and then had the same graph, because we're going to want to relate the inequality to 0 to positive and negative parts of the function, and then we can just look and see what's above or below the x-axis, so to speak. Okay. If we continue this example and actually solve it analytically, we're going to notice that the zeros divide the x-axis into 3 intervals. The zeros are at -1 and 4, and so we can see we actually have 3 sections of the x-axis, 1, 2, and 3. These intervals go from -infinity to -1. The second interval goes from -1 to 4, and the third interval goes from 4 to infinity. When we divide the x-axis, we know that the sign of a function is the same for all values of x in a given interval. So the sign in each interval does not change. It changes at these 0 points. And we can see that from the graph, right? Because at the zeros are where it crosses over the x-axis, or it hits it and bounces back, if you remember multiplicity from before. But in either case, it's a 0 at those 0 points or critical values we're going to look at in a minute. And we're looking at what's happening in the interval between these points. So that's exactly what we're going to do. We can choose a test value for x from each interval. So for example, in this first interval, we're going from negative infinity to -1. So we need a value that's in this interval, -2, -3, -4. We don't pick any of the endpoint values. We don't pick -1, we don't pick negative infinity. Between -1 and 4, we could pick 0, we could put -1/2, we could put 0, 1, 2, 3. Usually it's a good idea to pick an integer value. And if 0 is in your interval, pick that one because that usually makes it really easy to solve. And in the last interval, we're going from 4 to infinity. So we could pick any value we want. We could pick 4. I'm sorry, we can't pick 4 because that's an endpoint. But we could pick 5, 6, 7, 10, whatever. Okay? So we want to pick a value in each of these. Now, why do we do that? So if we pick -2, we get the answer 6. If we pick the value 0, we get -4. And if we pick the value 5, we get +6. Because what that does is it tells us what's happening in that interval, whether it's positive or negative. And we can see in the first interval it's positive, in the second interval it's negative, and in the third interval it's positive again. Now, the solution set consists of the interval where the sign of f of x is positive, because remember the equation asked us, where is this function greater than 0? So it's asking us, where is this function positive? Well, we can see it's positive between -infinity and -1, and between 4 and infinity. So our solution set is, in set notation, it's described as x such that x is less than -1 or x is greater than 4. Or in interval notation, it's parenthesis -infinity comma -1 parenthesis union -4 comma infinity parenthesis. And you can see those two sections highlighted there with the circles. So to solve a polynomial inequality, what we're going to do is to find or rewrite an equivalent inequality with p of x on one side and 0 on one side. Now in the last example, this was already done, and I mentioned that if it had a number on the right side instead of 0, we would have moved that number to the other side by adding or subtracting, depending upon whether it was positive or negative. Then we're going to solve the related polynomial equation. We're going to find the zeros of the equation. So we set the equation equal to 0 and find the zeros. Where does the function actually cross the x-axis? We're going to use the solution to divide the x-axis into intervals like we just did, like a single number line. And then we're going to select a test value from each interval and determine the polynomial sign on that interval. Your calculator is great from this because you can just plug it into your calculator and do the y equals, and then you have a whole table function that can show you values, so you don't have to keep calculating them over and over again. And then simply determine the intervals for which the inequality is satisfied and write it in interval notation or set builder notation for the solution set. Remember to include the intervals in the solution set if the inequality symbol is less than or equal to or greater than or equal to, okay? Remember to include them when you have the greater than or equal to or less than or equal to. If it's just less than or greater than, we don't add those zeros, remember? Because 0 is where it crosses the x-axis and the function equals 0. So if it said greater than or equal to 0, we would include it. If it just said greater than, we would not. And that's all this number 4 is saying. So remember, when we're using interval notation, we have to use, if we're including it for these symbols, we use the square brackets, and if it was just greater than or less than, we would use parentheses. So now let's look at an example which is set up so that it's not equal to or less, not less than or equal to 0. Because that's just one of the ones where we have to manipulate the equation first so that we have 0 on one side. So the first thing we're going to do is subtract 15x from both sides, so that will then we'll have an equation, an equivalent expression that's less than or equal to 0. We'll then use that by changing it to the less than or equal to 0 to equal to 0 and finding the zeros. So again, the first thing we want to do is set up the equation so that 0 is on one side. And all we had to do is subtract 15x from both sides. We change the less than or equal to an equal sign so that we can then find the zeros of the function so that we can see where the graph is actually crossing the x-axis and going above or below 0, which is why we set up the equation in this way to begin with. So if we factor the equation, we see that we have three factors, x, 4x plus 5, and x minus 3. If any of these factors equals 0, then we have zeros of the function. So we set each of them equal to 0, and we can find that the zeros are 0 when the factor is x. It's 3 when the factor is x minus 3, because x minus 3 equals 0 is true when x is 3. And then 4x plus 5 gives us 0 when x equals negative 5/4. And so we can also see that if we have these zeros, then we have three x-intercepts, which is 0, 0, 3, 0, and negative 5/4. Notice because we have 3 points, this actually divides the x-axis into 4 sections before and after each point. So what we need to do is determine a value in each of these intervals. So negative 5/4 is our farthest left. So our first interval is from negative infinity to negative 5/4. And then our next interval goes from negative 5/4 to 0. And then our next interval goes from 0 to 3. And then, of course, from 3 to infinity. And you can see all those here, right? We have 3 zeros, so we're going to have 4 intervals, okay? We need to find a value in each interval, so we picked negative 2 in the first one and calculated the functional value. Between negative 5/4 and 0 is negative 1, so we can use that value, and we found that the y value or the function value is 4. Between 0 and 3 we picked 1, and the value is negative 18. And between 3 and infinity we picked the value 4, x equals 4, and calculated the function value. So we can see that the function goes from negative to positive to negative to positive as we go throughout all these intervals. Well, remember that we're looking for where the function is less than or equal to 0. So we're looking for where it is negative. So there's 2 intervals here between negative infinity and negative 5/4, and between 0 and 3. Now remember that when the symbol is less than or equal to, we have to include the 0 values as part of the answer, because it's not just asking where it's negative, but also where it equals to 0, and we know the function equals zeros here. So when we're documenting the solution in interval notation, we need to use square brackets for all of these answers. So our final solution here is x such that x is between negative infinity and negative 5/4, including negative 5/4, or where x is between or including 0 and 3. In interval notation, we get parenthesis, negative infinity, comma, negative 5/4, bracket, union, bracket, 0, comma, 3, bracket. Okay, it's very important that you pay attention to whatever inequality, and if it's less than or equal to, you have to include the values for the zeros. Let's try another one. X cubed minus x is greater than 0. Well, we already have 0 on one side, so that's in good shape. So now all we have to do is find all the zeros. Now, this is actually kind of bad notation. We should have turned this greater than into is equal to actually solve for the zeros. So this is a little bit of a misnomer, but we have factored it. And if we think about when do all 3 of these factors equal 0, when do each of them equal 0, we can find our 3 zeros. And we get negative 1, 0, and 1. We use the zeros to find the values in intervals, and we can again see that we have 4 intervals, 1, 2, 3, 4. If you have to draw a number line, that can help. And so notice that our intervals are from negative infinity to negative 1, from negative 1 to 0, from 0 to 1, and from 1 to positive infinity. Don't stop at 2, it continues on. There's no dot at 2, so it continues on to positive infinity. We don't have to worry about any of the 0 values because our inequality is simply greater than. It's not greater than or equal to, so we're not going to include any of these endpoints. There are all the intervals, the 4 intervals that we have. So now we have to find test values in each. Again, not using the endpoints, but some value in between each of these endpoints. Notice because we go from -1 and 0, we have to find a fractional value, and here we've used -1/2. In the same case between 0 and 1, there are no whole numbers, so we're going to have to use a fraction, which can be a pain in the butt, but you have a calculator. And you also can use the calculator function value. And between 1 and infinity, we pick 2. Here we can see that the function goes from negative to positive to negative to positive, and in this case we are looking for positive results. When is the function positive? So it's positive in this interval, and it's positive in this interval, the interval between -1 and 0, and between 1 and infinity. Again, we can see that by the signs here. So our solution is, in interval notation, it's parenthesis -1 comma 0 parenthesis union parenthesis 1 comma infinity parenthesis. That's documenting where it's positive between -1 and 0 parenthesis -1 comma 0, and then of course parenthesis 1 comma positive infinity parenthesis. All right. In set notation, it's x such that -1 is less than x, which is less than 0, or x is greater than 1. Okay. So we're going to do the same thing for all of these polynomial inequalities. Find the zeros, use the zeros to divide the x-axis into intervals, find test values in each interval, determine whether they're positive or negative, and then use that to find the solution. The tricky part again is to remember if it's greater than or equal to, that you have to include any of the 0 points when you're documenting them in the solution. If we look at the graph, we can see that indeed the graph is positive or blue here between -1 and 0, and when x is greater than 1. Now we're going to look at rational inequalities. Remember, rational expressions, rational equations are where we have a polynomial in the numerator and a polynomial in the denominator, or basically simply a fraction, if you will. What we're going to do here is we're going to find an equivalent equality with 0 on one side. So again, this is just saying if we had something here, like if it was greater than or equal to 4, then we would have to subtract that 4 from both sides. Okay? Then we're going to find the zeros. Now, the best thing to do is to remember that fractions equal 0 if the numerator equals 0. So as long as you just have a simple fraction on one side and the 0 on the other, all you have to do is set the numerator equal to 0. If you have a fraction plus or a constant or something, you can make it into one fraction, or it's going to be a little bit more involved. Then we're going to find the domain, find the values of the variable for which the related rational function is not defined. And remember, fractions again don't exist. That's what DNA means, does not exist or undefined, if the denominator equals 0. Okay, so we can set the denominator equal to 0 and solve for x values of that. So these can be quite simple. We're going to set the numerator equal to 0 to find the zeros. We're going to set the denominator equal to find the places where it doesn't exist, if we have a simple fraction on the left side or on one side. These numbers that we found in step 2 and 3 are what's called critical values. And these critical values, before we just use the zeros in polynomial inequalities to separate the number line into intervals, here we have to use all of the critical values. Not only the zeros that we found in step 2, but also the values of x that make the equation not exist. Once we've done that, we're going to select the intervals for which the inequality is satisfied. Is it positive? Is it negative? We're going to plug in test values to figure that out. Just like before, if the inequality symbol is less than or equal to or greater than or equal to, then we have to include the 0 values using a square bracket or using the greater than or equal to or less than or equal to language in our set notation. Do note that the x values in the domain, or where the function does not exist, will never be included because those are what make the whole function unsolvable. So let's look at a problem here. Solve x plus 3 divided by x squared minus 1 is greater than or equal to 0. So the first step is already done because we have 0 on one side. This can get a little more complicated if it was a number here, or even if it was greater than or equal to x, we'd have to subtract x from both sides, and then we'd have to make this into one fraction. So the first thing we're going to do is find the zeros of this function, and that is where the numerator equals 0. And so for this we get x equals -3. Then we're going to find where the function doesn't exist, and this is by setting the denominator equal to 0. And we get x squared minus 1 equals 0, which gives us x squared equals +1, or x equals the square root of the positive or negative square root of 1, or x equals positive or -1. This gives us three critical values. Remember, these are the answers to these above steps. So we have -3, -1, and +1, which separates our interval into our number line into four intervals, from -infinity to -3, from -3 to -1, from -1 to 1, and from 1 to infinity. We find a value of x in each of these. We use -4, -2, 0, and 2. Use small values, use easy values. 0 is often an easy value to calculate. And then what we're looking for is we're not so much concerned about the value as the sign. So here we can see in the first interval it's negative, then it's positive, then it's negative, then it's positive. And what are we looking for in this problem? We are looking for values where it is positive because it's greater than 0, or values that are where it's 0, which is only that one value, which is -3. So we have to remember we have to include -3 in our solution. Based upon this, we can then determine the solution. We know it's interval -3 to -1, and from 1 to infinity. The function is positive in the intervals -3 to -1 and 1 to infinity. Since -1 is not in the domain of f, it cannot be part of the solution set, but note that -3 does satisfy the inequality because it does equal 0. And so we get the solution set is bracket -3, comma -1, parenthesis. Again, we include the 0, but we do not include the domain part of the problem. Union, parenthesis 1, comma infinity. And again, we don't include the value of 1 because it's not a 0. It's possible to include the zeros when we have greater than or equal to or less than or equal to, but we never include the values that make the function undefined. All right, well, that's the end of today's lecture. It wasn't so long, I hope. And if you have any questions, please reach out.